Okay, so I work on optimal control. I used to focus on biological motor control. More recently, I've been doing more control theory and applications to robotics. The specific aspects of control that I'm going to talk about today have to do with contact dynamics. And if you look at sort of early applications of not only optimal control, but control in general, it kind of came from aerospace, where the idea is to not make contact with anything because that would be really bad for you. When people started doing control of sort of machinery and robots and such, contact with the environment is unavoidable, but still most of the time the idea is to avoid contact. So you either do collision avoidance, or if you have to weld something or whatever, you carefully plan the only point of contact that's going to happen, and you kind of treat that as separate, and the rest is still a collision-free problem. In contrast, if you look at how biological systems navigate the world, they push all kinds of things, they use all kinds of crazy non-prehensile manipulation strategies, they can lean themselves on things. So biological systems have found ways to embrace the complexity of contact dynamics and actually take advantage of it. And robots will have to do the same at some point. What that means is that you somehow have to plan through those contact dynamics, meaning that when you're trying to build a system that actually works, you have to consider somehow what these contact dynamics are doing for you. So I mean, in my lab, a lot of people have been working on this recently, trying to figure out how to take the complexity of contacts which are intermittent and nasty and make the system discontinuous and combine it with optimization. Now, the general idea of optimal control, like when you actually try to do that in practice, there's sort of three ingredients. One is the cost function, the thing that you're going to optimize. And then you usually integrate it over time, maybe under sub-constraints, and you need some optimization algorithm that is going to do it for you. And then you have a dynamical system, which you can write in this general form. Now, if you look at the literature on control optimization, usually people focus here. You know, they're like if you open up the proceedings of the CDC, Conference on Decision and Control, somebody develops an algorithm, and then on the last page there's a numerical example where they roll down a little dynamical system, little cost function, and just show the algorithm works. Now, if you try to scale that to larger systems, and I should say I was one of the people writing these papers. Once you try to scale that to large systems, you realize that actually figuring out this thing and being able to simulate it and compute all the quantities that you need takes up almost all the time, both in terms of research and development and in terms of what your computer is actually doing. And so in everything I'm going to show you, there's a fast computer, the computing stuff. At least 80% of the computing power goes into evaluating the physics of the system and numerical derivatives that are needed for optimization. And there's a little bit of time spent on evaluating cost functions, and then the algorithm has to do something, but that's not really where the heavy lifting happens. So having realized that, I spent the last 6 years of my life developing a new physics simulator, which is designed to make this possible, to not only simulate physical systems, but also enable us to optimize through a general purpose simulator, especially one that has contact dynamics. I'm on sabbatical at the moment. I'm writing a book about this, and you're very welcome to read the book online, so I'm not going to go through details. I'll just give you some highlights. So the way this thing works is that it actually has its own language for specifying dynamical systems. So here's a 7-degree of freedom arm with a ball joint here and 2 hinge joints here and here. This is a free body that can move around. This is a string that has a length limit, so you can use it to like wave this around and throw it in the air, whatnot. And the point is that you need to write this little XML file to specify that dynamical system. And for humanoid, it will be slightly longer, but it's not as bad as you might have feared. And then this is given to a model compiler, so there's actually a compiler built in, and then it simulates it. So for those of you who are familiar with an old simulator called SDFast, which is a really good thing, this thing is a cross between SDFast and the modern gaming engines that handle contact dynamics, except this handles contact dynamics in a somewhat smarter way. Here's a little comparison that we did recently. So what we're going to do here is the following. Here's a robot arm with a hand, well, some kind of abstract arm in the hand. We apply squeezing force to keep the cylinder in the hand, and then we're going to generate random smooth torques that kind of wave the thing around. And the question is the object going to remain in the hand? So we know we're applying enough force and there is enough friction so that a real hand would keep the object there. And as with almost every example of numerical integration, if you make the time step really, really small, things are going to be accurate. But you don't want to make it too small because it's going to take you forever to compute anything. So the question is, how big can you make a time step before things break down? And this table here shows you the answer, and you can see that this is the simulator we're working with compared to a bunch of things that exist out there. It's almost 10 times bigger. You can illustrate that as a movie, and of course my movies don't work because this stupid PowerPoint. Okay, this is really bad. Can I just... Okay, sorry about it. Just give me a second here, I'll figure it out. That's what happens when you update to the latest software. They change things on you and you don't know it until it's too late. Use, okay. Does anyone see anything that says, please keep it simple and don't get in my way?
We have a black screen.
Huh?
We only have a black screen.
Oh, that's why. Automatic. Now work. And see, the problem with all of that is if I click on things, it won't play the movies that are behind them. What? Well, how am I supposed to do this?
To turn off the screen of your laptop, that's the simplest basic version.
That's a really good and simple bad idea, yeah. You're right, okay. Sorry about that, guys. This is really embarrassing, but okay. Which one is 1 and which one is 2?
It's not possible to run it out of PowerPoint.
Sorry? Well, because they had a bunch of movies in it. Okay, so this, thank you, Nicola. That was brilliant thinking. Okay, now I have a bit of a more control problem trying to calibrate my mouse movements, but other than that, good. Okay, so here's a little example of that. So these are a bunch of different physics engines. We start a small time step, and then we gradually increase the time step, and when a given engine drops the object, it's going to disappear. So these two disappear right now. This is the one from NVIDIA called physics, which is still surviving. It's going to drop it around here. And then these things happily keep going. So the point is that you need these large time steps to do planning in practice. And yeah, things can go crazy. You can also define something like a speed accuracy trade-off, which is based on the same general idea. So the idea is that you take any simulator you want, you integrate to a very, very tiny time step, like 1/64 of a millisecond, and you get a sort of a gold standard for that particular simulator. And then you start increasing the time step and see when does it deviate from its own standard, and you can plot a speed accuracy trade-off on log scale, and so the approach that we're using actually works really well by some orders of magnitude. So the key behind it is the treatment of contact dynamics. Now you might have thought that physicists have solved all these things, so why do I even bother talking to you about it? And the answer is that no, actually they're not solved. The reason they're not solved is because what we're trying to simulate is rigid body dynamics. And contacts are inherently non-rigid phenomena. When you do that, it might sound like they're rigid, but really it's all about the deformation of the little materials here. The only right way to do this is to solve a PDE, but nobody has the time to do that. So what we're trying to do is we're trying to tweak the laws of motion of rigid body systems to capture phenomenologically the underlying non-rigid phenomenon. And whenever you try to do that, you're obviously doing all kinds of approximations that are all bad in some way, but some are worse than others. So that's why this research field is actually still open. It's a fairly active literature on developing contact models of the physics of contact. In particular, all the modern models come down to an optimization problem. So both this simulator and all the simulators behind your favorite, first-person shooter games, what they do is they don't actually have an analytical formula for what the equations of motion should be, like even instantaneously. Instead, what they do is they solve an optimization problem at every time step to figure out what is the acceleration of the system in response to some applied force. And then they keep going. To make matters worse, the standard formulation is something called LCP, linear complementarity problem. So that optimization problem is in fact non-convex when you have friction. So it's shown that it can be NP hard. So on top of that, people introduce all kinds of approximations. What we've done here is turn this into a convex optimization problem by basically considering the fact that the contacts are soft. So again, I said I'm not going to go into the details of this. I just want to make the point that unless you handle those details, building up on top of it and using this as a tool is just a dead end, and it's not going to work. So unfortunately, the background sort of mundane work has to be done before we can build up on top of it. I'm just going to illustrate that the same sort of physics model can, by just turning the continuous parameter knobs on the model, can give you very different types of contacts. Some of them are hard, some of them are soft, some of them are bouncy, some of them looks like they're floating on a cushion. This is like an underdamped thing that takes a while to recover. And we need that for several reasons. One reason is that in optimization, you often want to do continuation. So you want to start with a soft contact model and then gradually make it harder and harder and track the solution as it progresses. Another one is that if you're doing system ID on a physical system that actually has soft finger pads or rubber things, whatever, you probably have to adjust the parameters of some models, which means that to do system ID, you actually need parameters that you can tweak. So it's good to have something that's parameterized. Okay, so we're going to be using these tools throughout the talk. Now, there are lots of ways to do optimal control. One of those is to focus on optimizing trajectories, which is what Jean-Paul talked about, and which is what my talk is also mostly about. But it should be clear that that's only one way to do it. So that comes from Pontryagin's maximum principle. There is another school of thought which is based on dynamic programming and the Bellman optimality principle. And what that says is that you should be computing a global feedback control law, or alternatively a optimal value function over the entire state space. And it's a much harder problem to solve, but once you solve it, then you know what to do everywhere. Of course, in practice, that thing is hard to scale to any interesting problems, which is why I have temporarily given up on it after writing lots of papers on how to do it. So for the purposes of this talk, we're going to focus on trajectories. Now we're going to think of this as a black box, which is an optimization machine. It has some computer code sitting on top of some math. It's basically going to be an optimizer. I'm not going to talk about that anymore. Now we just want to use it. So the inputs to it are a physics model. Let's say this humanoid here. You have to put in some costs and constraints. So in this case, for example, we're going to say that we're trying to model walking. So we're going to just come up with a simple model of energy, which is a torque squared. And we'll try to minimize this over time. And we're going to constrain the velocity of the torso. We're going to say that I want you to move forward at whatever, 2 meters per second, while minimizing this. And we're going to parameterize joint angles in a Fourier basis because we know the thing is periodic. So that's a way to actually put in some priors into the optimization. And we're just going to search for all the joint trajectories such that in this case, if we do inverse dynamics on them and evaluate this cost is going to be as small as possible. And so this really simple-minded problem formulation gives you things that look a lot like biological walking. So this thing is handling all the contacts, all the joint interaction forces. It maintains a pose that's not statically stable, but it catches itself every time so it doesn't fall, and so on. So, so we can do that. And as Jean-Paul also told you, you can, like, if you really want to solve these optimization problems, you can. The question is, how do you do it efficiently in a way that will allow you to actually use these things in practice? So we spent a lot of time designing more efficient optimization methods. And if you look at numerical optimization, it's kind of a shame that in the past few centuries, there is not any like qualitative improvement really. I mean, we're back to Newton's method, which is where we started. Even the fancy like interior point methods nowadays that people can prove theorems about, that's great, but at the end of the day, it's just Newton's method applied to a weird cost function that just blows up at the boundary. So after trying to develop a few fancy optimization methods ourselves, we kind of realized that really what you need to do is to develop better problem formulations and not better optimizers. Because with the optimizers, we've kind of hit a brick wall. But there is a lot of room for improvement in how you formulate your optimization problems. Some formulations allow the existing optimizers to find amazing solutions very quickly. Others will get them stuck in local minima, and you'll never be able to make progress. So we've turned the sort of problem formulation into a science in a way, and that's where a lot of progress comes from. So here's one example of these methods. We call it contact invariant optimization. And this is based on the realization that if you are manipulating the world, or let's say here you try to get up there, the red things denote which body parts are in contact with the environment. And depending on what combination of body parts or parts of body parts are in contact, that determines some continuous dynamics. And then when you change that configuration, the equations of motion change in some structural way. So basically, there's a combinatorial number of dynamical systems you could be working with, depending on what subset of things are in contact. And combinatorial searches are usually bad for business, so we want to avoid them. Now, some people embrace them and handle them bravely. Actually, some people here in us have been developing methods to do that with sampling and such, and they don't seem as hopeless as I would have thought. But still, it's good to go to continuous optimization. In fact, a lot of the powerful methods for integer programming these days have to do with relaxation and figuring out how to turn a discrete or combinatorial search into a continuous one, and then just push it to the limits where it becomes discrete. So this is what this method does. Basically, this is a domain-specific relaxation method to turn the discrete optimization problem into a continuous one. So technically, the way to do it is this. So we relax the problem a little bit. We allow the optimizer to search for a sequence of body configurations Q over time. So that will be called the trajectory, and the sequence of contact forces. Okay, so we allow it to explicitly plan contact forces. If we're given those two, we can do what's known as inverse dynamics. So this is mass times inertia. These are Coriolis centripetal gravitational forces. This is the contact Jacobian. This tells you how contact forces map to joint forces through the inverse Jacobian. Once we know this F, because it's an optimization variable, we can do the inverse dynamics and get the control signals that you must have applied to make that happen. And so now that we have the trajectory and the forces and the controls, we can form whatever cost function we want and optimize it. So the cost functions here are things that saying there's a task cost that basically says what you want to, like get your hand to an object or get out of the door or whatever. Control costs usually penalize energy. There are things that penalize non-penetration, and this is the important one. This is the continuation trick. So we're allowing contacts to act from a distance. Okay. So this is the normal force at the contact. This is the distance between where you are and where is the thing that you're touching. And we multiply those two, right? So if the distance is not 0, then this is going to be big. So it's some kind of penalty. But how big that penalty is depends on the continuation parameter. So if I set this continuation parameter to 0, that means I'm allowed to push things from a distance like a Jedi and make things happen, which will be very convenient for me, except it's not realistic. But that's an easy problem to solve. Optimizer will really figure out how to optimize the movements of a Jedi because he doesn't have to do much. He just thinks about it and things happen, right? So that's easy. And then as we start to increase this continuation parameter, we're forcing the physics to become more and more realistic, and we're telling you, well, if you really want to push something, you have to touch it first. You can't push from a distance. Okay, and then as we do that, we force the solution to converge to something that's realistic. So let's look at a number of examples of this. So here's this wishful thinking phase. Here, this guy is kind of imagining himself floating through the air. And then we turn up the continuation and says, oh, well, I can't really do that. I have to touch the ground somewhere. And then it cleans up the movement into kind of semi-discrete motions. And then we're just playing the movie. So everything I'm going to show you here, the optimization, the entire movie is the optimization object, basically. We're optimizing the sequence of poses over time and the sequence of contact forces over time as one big object. So it has like several thousand variables in it. It takes on the order of 5 minutes of CPU time to generate one of those. So the cost functions are really simple. So there's a cross here. The cost function says, start at the given initial condition, put your body over the target, and minimize accelerations of the joints in this case, I think. Okay? And all the details of this come from the interaction between the physics and geometry and your optimizer and this really simple cost function. Here's a task that says, please put the object down there, and the cost function doesn't even mention the fact that there are people in the room, but the optimizer knows that the object is not actuated, so you have to use those people to do something. Here, this says, put your head up there. Here, the cost function says, make the tip of that object trace that square, and the thing figures out that it has to use its hand, grab it, and move it around. Here, the cost function says, make the object spin in the vertical plane. We don't care about your hand, just make it happen. And all of that emerges. out of it. Same cost function, but now there are not enough fingers. So the optimizer figures out that it has to use the table for support, because otherwise the spinning thing just won't happen with that many fingers on your hand. So as you can see, this is a really universal method that can work for hands and full bodies and whatnot, and for various tasks. Obviously, it wasn't very detailed. So then we moved to a much more detailed biomechanical model, actually. So this we modeled a number of muscle groups in the lower body, and there are things called hill-type models that just curve fits to muscle physiology that are very accurate. Here we're using models of energy consumption that come from a biomechanics, so we're very careful to not touch the cost function here, because that could allow you to fit. So basically we say, okay, we're going to take these metabolic energy models, use them as they are, and just apply the same algorithm to the level of a musculoskeletal system. And this is what happens. So here's a guy walking. So in all these simulations, the lower legs have muscles in them. So you can see that the muscle and tendon stretch relative to each other, which is what real muscles do. And the red things mean that the optimizer decided to activate some muscle at some point in time. You notice that the upper body is kind of stiff, and that's because the upper body is torque controlled. We just haven't put muscles yet. But the lower legs are very realistic. So this is really, I mean, you can think of it as optimal control work. You can also think of it as from first principles explaining human motion. It's because we said, here's the body, here's a bunch of muscles, here's a notion of metabolic energy that came from empirical measurements, and we didn't touch that. All we did is we put a high-level cost function that said, for example, in the case of walking, it said, move your head forward at 2 meters per second, and other than that, we don't care, do whatever you want. And so all of those details emerge out of that. Here's actually a comparison to experimental data. Here's walking speed. The white pink things is data collected at, I guess it's called Delp's lab, or affiliate researchers at Stanford. So they have lots of people walking on treadmills, and they do all the kinematics and dynamics. These are joint angles. These are torques. These are some EMG activities. For running, it's not so close, but I mean, you can see that it gets a general pattern from first principles. So summary so far, we can use trajectory optimization to get surprisingly rich and complex movements involving elaborate contact dynamics without any help from manual scripting or tuning or motion capture or any such thing. We can use generic optimization methods, LBFGS or Gauss-Newton. Gauss-Newton is our favorite at the moment. Well, let me not get into details. So the optimization is generic, but the way we formulate the problem, and in particular the way we handle the physics of contact is the key. That's what makes these things work. So I should say that it's not like people haven't tried these for decades, but the people who have tried knew that they're going to get stuck in local minima, so they didn't even publish their failed attempts until relatively recently. Our group and a number of other groups started to realize that, wait a minute, computers are fast enough and we're clever enough in handling the physics of contact that we can actually make this possible, and we can embrace the contacts and not shy away from them. Now, it takes about 1,000 iterations of a Gauss-Newton method to discover these things from scratch without not knowing anything, which takes around 5 minutes of CPU time on a good workstation. So that's good, but if we want to use this for real-time control, we have to obviously do something else. We cannot sit there and think for 5 minutes before we move, although some robots have done that. In fact, most of the fancy robot demos that you see nowadays are exactly that. In fact, it's not even 5 minutes. It's weeks or sometimes months of the fine-tuning of students and postdocs and technicians and brave people who work really hard to make one demo happen, and then it happens, and then it's videotaped and put on YouTube and move on to the next one. As a result of that, humanoid robots are a curiosity in research labs, but good luck selling a product that's based on 3 months of manual tuning for one movement. That's not going to happen. So if we ever want to go beyond the demo stage, we really have to automate this process, and it has to become an off-the-shelf technology and not just a research project every time. And so that's what sort of we want to accomplish. And so I'm going to talk about 2 ways of doing that. One is just basically do it in real time, really fast. It's called model predictive control or receding horizon control. Preview control is another word that people in robotics, I guess, introduced for no good reason, because there were already all the terminologies that refer to the same thing, but anyway. So the idea is really simple. You're somewhere. you're going to optimize, let's say, up to 1 second in the future, and you're going to sum up all the cost, or whatever state and control cost. You may evaluate some final cost, which is often heuristic. And then we're going to solve this trajectory optimization problem really, really fast, let's say in 20 milliseconds. Okay? And then we'll start executing this trajectory, and then things are going to deviate from the plan. So the blue is the plan, the red is what actually happens. Why is it deviating? Well, because the world is not perfect. Our model is not right. That's okay, because a little bit later we're going to sense the world, and wherever we are, we're going to start another trajectory optimizer at that point and make another plan and keep going. So this is a very popular methodology. Actually, it's one of the oldest tricks in the control book, really. It's routinely applied to things like chemical plants because their dynamics are slow and smooth enough so that your optimizer can outrun the real-time clock. So obviously here the catch is, can you optimize faster than the real world is moving forward? Like if you can, then you're in business. If you cannot, then forget it. There are lots of examples of that. So for example, if you look at all the computer chess or any other games that computers play, that's basically what they do, right? So they have a model of, let's say, the chess dynamics. They have a cost function, which in this case just says, did I win or did I lose, plus some heuristic that they put in here. They unfold the game dynamics, they do some analysis, and then say, okay, given the plan that we've made up right now, here's the best move. Then we see what the opponent does. That means, the opponent did this, and then we plan again. The difference is that in things like chess, there's actually discrete world of possibilities, and usually there's search trees and various heuristics to prune them. Here we're dealing with continuous world where the tree is infinite, so we can't really do that. So instead of that, you think of this as just only one branch through that tree, which we're continuously optimizing with gradient descent. But the concept is really the same, and the mathematics behind it is basically dynamic programming. So when you put all this together and implement it carefully, it actually works. So I'll start from some simple examples and then to go to more complicated ones. So here's a 3-degree of freedom robot. There are Vicon cameras looking at these balls. They think they're markers. The cost function says, please hit the ball in such a way that it comes back, basically. And other than that, do whatever you want. Here's simulations. Here the cost function says, put your nose at the green thing and stay away from the red thing because it's scary. And so these movements emerge completely on the fly. So going back to a question someone asked, are these things planned or not? Well, you see how the notion of planning is a concept that we have in our heads, but maybe not that relevant to the real world. So these are planned, yes, but they're planned only half a second in the future. And then the motion that actually emerges is the result of interaction between your ongoing planning and replanning and external perturbations that we deliver here with this red arrow, for example. So here the cost function says keep your body over the feet and don't move too much. So basically stand still. And this thing invents crazy acrobatic maneuvers to save itself and stand still. Here are examples of in the VRC where we're planning through one physics engine, which is ours, and then running the plan in a different physics engine, which is ODE, as implemented in the gazebo simulator. Here cost function says keep your head pointed at this thing, which we manipulate with a joystick. And then this figures out what to do with the body. And again, everything I'm showing you here is computed in real time. It's fully interactive. Here the cost function says, make this object go somewhere in space. Okay, that's it. And the thing has to figure out how to basically grasp it. So you can see that there are all kinds of extraneous movements with the fingers that your hand probably couldn't even do. And that's because we don't have biomechanical constraints here. It's just a 20-some degree of freedom hand. This is an example where it didn't actually work so well. So our goal is to have finger, like robots, manipulate an object and make it do whatever we want. And we succeeded at some things. For example, here we can throw in really bad perturbations, moving the base of a robot, which is usually a no-no in robotics, but we can handle it. This is something that I'm not going to talk about. So in this case that I showed you with the fingers, turned out that in simulation, it's all good, but when you try to put it on the real system, the models and the estimation is not accurate enough to really give us the performance we want, and I'll come back to that later. But at least in simulation, we can do pretty amazing things in real time. And computers are only getting faster. So that's another beautiful thing about this approach. You can sit around and do nothing, and 10 years from now, your results are going to be a lot better than they are today, just because Moore's law keeps going and Intel keeps adding cores to your processor. And this is massively parallel. Like you can run every time step of the simulation on a different core. Within each time step, you can use multiple threads to do finite differencing. So it scales naturally with the increasing speed of computers. So we don't even have to do anything. We can just keep writing papers about, oh, the latest computer did this. So it's really good in terms of publishing, actually. Now, one disclaimer here is that getting these things to optimize in real time, you actually have to design the cost function somewhat carefully. In the first set of simulations I showed you where this guy was going over the cross, that was really simple. We said, okay, the cross is over there, put your body over there, I don't care how. And when the optimizer had 1,000 iterations of a Gauss-Newton method to figure it out, it does figure it out, right? So if you want to start with a very simple and high-level and intuitive cost, you have to pay a price in terms of computation to figure it out. If you want your optimizer to nail it like in 1 or 2 iterations, then you kind of have to help it. So basically, you have to give it something that's in between a high-level cost function and something more like a heuristic value function. So having realized that, we actually developed a machinery to experiment with these things very quickly. So we realized that most cost functions that we and others use in practice are in this general form. So you have the state of the system, you have the control signals. You define any function of those two things, you call a feature, whatever that is, some quantity of interest that you believe is important. You specify a reference value for that feature, and it may change over time. You subtract the two, you get a residual. You use a norm to compress that residual down to a scalar, and you can have many norms that you want. Weight them with some scalar coefficients, and that's your cost. Okay? And so now what we do is we have a file format for describing these things. We say, okay, so please go get me the center of inertia of the pelvis and get its z elevation, whatever, multiplied by 1. And then what we have is we actually have this user interface that allows us to tweak those coefficients in real time. And we can see how the behavior itself changes as we change the cost function. So here's the guy that's riding a unicycle. He can put torque on the wheel. The cost function right now says don't move too much, stay over the wheel, and keep energy small. Now what we're going to do is we're going to change one of the cost terms that says don't move too much. Okay? And see what happened. He adopted instantly a different, sort of qualitatively different strategy for balancing, just by making a continuous change in that cost function. That's because we said moving is bad. Now we're going to enable another term which says reach for a target that's somewhere out there. So once we do that, the optimizer will start figuring out. So right now that it's sitting here, it's actually the optimizer is thinking that's why it's sitting, because it hasn't figured it out. And then it finds a good local minimum and figures out that means driving to a target and stopping there. So this is actually an interesting way to think about hierarchical control. So if you want to have some low-level control that does the heavy lifting for you, and something high-level that's more intuitive and that has a few knobs that you can tweak, what should those knobs be, and what should be the language that these two things use to talk to each other? And I think the coefficients of a rich and elaborate cost function are a natural way to do that, because all these terms, they actually have intuitive meaning. So this is energy, this means balancing, like don't fall, reaching a target, whatever. You can actually ascribe cognitive meaning to them and then say, okay, I care about balancing more than reaching right now. And you can instantly see what that means in terms of the actual motions. So anyway, so that's one way towards making these things run in real time. And it has its limitations, like I said. You cannot make these things stretch too much in the future because you run out of CPU time, but that's only getting better. Now, another way to do it is to solve a lot of these optimization problems and cache them into a big neural network. So you can think of a neural network as a function approximator that has hundreds of thousands of free parameters. And by tuning those parameters with gradient descent, you can get it to fit pretty much any function you want. As you probably know, this has been very successful in all kinds of areas. It started with computer vision, where we now have state-of-the-art vision systems that are just going from pixels to high-level object classification with nothing than big neural network. And it's applied to natural language processing and forecasting of all kinds of things. There's a whole industry. That's why Google and Facebook and Microsoft are just buying every machine learning technology they get their hands on right now. So if you want to get rich, just develop a neural network algorithm and publish it at NIPS. And I'm told that it's basically an ongoing recruiting party for these big companies. And I'm not joking, actually. So we're kind of going to use this here. We're going to train a neural network that is control policy or a kind of a reactive feedback controller. Something that most of you will say that it does not do planning. So what does it do? This is the state of the body. This is its own internal state, something like a memory of what happened recently. It pushes that through a big feed-forward mapping. There are a bunch of units connected with a bunch of other units. And it tells us what the next stage is going to be. And then we integrate that one step forward. Then we take whatever happened, feed it back here, and then we integrate. So it's a fully reactive controller. We're training that in the following way. So we use the trajectory optimizer, the one I showed you earlier, to help train the neural network. In particular, we're going to train about 1,000 short pieces of trajectories that I'm going to show you later what they look like. And then these are going to become training data for the neural network. The neural network is just going to solve what's called a supervised learning problem, which basically says I want to replicate that data. Meaning that given what happened here and here, I have to figure out what the weights are that instantiate this mapping. And if I have 1,000 trajectories, that's enough to constrain the weights. Okay? Interesting thing that happens is turns out you cannot just generate the data once and learn from it, because that's a very hard learning task for the network. Instead, what we discovered is that you really have to use the optimizer more like a teacher. So what it does is it looks at the network, it asks it what it would like to do, and it does some silly movements, and then takes those movements and says, okay, here's how to make them a little bit better. Not all the way to optimal, just a little bit better. Now take those and learn from them. And the network learns a little bit. And now it does something slightly better. And then the optimizer says, okay, give me your movements. Now here I'm going to improve them a little bit more for you. Now here, learn from them again. And you keep iterating. It actually happens in the cloud if you want to do it fast. So there are about 30 servers doing trajectory optimization. One big GPU that's training the neural network. It takes about 2.5 hours in the Amazon cloud to train a network with 250,000 weights. The data set kind of has to be diverse to span the behavioral range of things you want to do. So the way you generate that is you have some starting state, and you put some goal, and there's some optimal trajectory. Then somewhere in between that, you declare that to be another starting state, put a goal there, and you kind of get a behavioral tree spanning things. We also look at feedback. So we say, okay, what's the optimal response to a perturbation, and let's get the network to learn that. And we do that by actually getting the gradients of the network to be right. So we train the network to learn the optimal feedback gains and not just the nominal behavior. Okay, so putting all these together, we get this. This is going to be presented at NIPS about a month from now. So here's a simple thing. It's a jellyfish. In some simulation of swimming, this is a bird. The target is something we control with a joystick, and the neural network is making the physical system do whatever is needed to follow the target in this case. So the target is another input to the network, which we get to control in real time. Here the input to the network is, again, a target for the body, and it's a fully reactive thing that steps around. So again, all the planning that we did explicitly was cached into the network in those 250,000 weights. At runtime, you can ask, is this thing planning? And my honest answer is I have absolutely no idea. It's evaluating a big function whose consequence is indistinguishable from planning. Do you want to call it planning? Up to you. Here's how your sofa might walk. Here's some kind of donkey-like thing. Here's a spider. So exactly the same algorithm. You can run it on any body morphology and all kinds of cost functions, and it just works. Same network architecture as well, just the weights change. Here are the little pieces of trajectories. So we have 1,000 of those training the network. Now I should say that some people have been trying to do that completely from scratch without the help of a trajectory optimizer, notably the group at DeepMind that was acquired by Google. Some of my former postdocs are there. So they've been trying to do that, and people in Peter Abill's lab in Berkeley have also been trying that. Basically, the idea is forget about trajectory optimization. Just take a big neural network and train it brute force, basically. And their results are not at this level yet. I mean, they can control planar things. They can do some getting up, but what the behavior we're getting is substantially better than what they've been able to get right now. And actually, it looks a bit like floppy and random, almost like what MPC does. So there is really something about this notion of having a thoughtful optimizer help the network. If you don't do that, it kind of works, but it's not the same thing. It's also a lot slower, actually. But maybe there's going to be more progress in that area. Anyway, so the point is that big neural networks are very promising as control architectures, and there's no hope of analyzing what they do, but that's not a reason not to use them. In fact, we should use them. Now, in the next 10 minutes or so, I want to talk about transferring this to physical systems. So the obvious way to start is to build the most accurate model of the system you can, and also build the most accurate state estimator that you can that processes your sensory data. And then once you do that, you plug in your model-based controller, and you basically keep your fingers crossed. Before I get to that, why do you have to keep your fingers crossed? Can you do some math? And the answer is yes and no. There is a field called robust control that tries to do exactly that. So robust control was born as a reaction to the fact that optimal control didn't quite work when people tried to take it from aerospace and put it on land, basically. Because it turned out that if your model is wrong, the optimal solution for one system makes another system unstable. And the two systems don't have to be very different from each other. Okay, so people realized that and said, well, wait a minute, we have to do something else. So robust control is the idea that we're not going to optimize expected performance. What we're going to do is we're going to put some bounds on the disturbances or model errors and try to guarantee that if the physical system is within those bounds, then our control performance is going to be within some other bounds. And there are things called small gains theorems that tell you what's the mapping between the input disturbance and the output disturbance. And that's very good, except the only practical tools that exist, they exist for linear systems. Once you go to this general case, it's not clear what you can actually do, unfortunately. So in some sense, you can think of it as we're kind of doing that computationally, and some ways to do it is instead of looking at average performance, you can, for example, you can look at worst case performance or some kind of soft max that penalizes bad trajectories more than rewarding good ones. So it's not like either or. I mean, you could do things in between optimal control and robust control, which is basically they're all optimal control, but with respect to different cost functions. So anyway, I'm saying it's not that you have to keep your fingers crossed in principle. Just in practice, that's the reality. You can't really get bounds on interesting systems. So anyway, so here is what we want to do. We want to identify contact parameters and all interactions. So we're going to use teleoperation. We're going to use this phantom to make this phantom play with this object. There's an IMU here, there's a force sensor here, there are potentiometers. And we really want to explain everything. We want to build a physics model that explains every single thing that happened and every little bit of data that we collected here. Now, what we'll have to do is there are two sets of unknowns here. One is the model parameters, which are things like contact parameters that I referred to earlier, and then there are like some stiffnesses in this thing, and the actual physical dimensions and such, inertias, gains on the motor system. So that's the things that we want to infer from the data, and this is called system identification. But they're also the actual motions. You don't really know what they are. I mean, you have sensors, actually, have very accurate sensors, but still they may not be exact. And that turns out to be a real problem here. Now, you might have thought that you can collect a bunch of data, fix it, and pretend that you know what the real trajectories of the system were, and then do inverse dynamics or whatever, do system ID on it. And in general, yes, for simple systems like a fixed base actuator that just moves around, that's okay. When you have contacts, the problem is that suppose your trajectory estimator data processing thing made an error of even 1 millimeter. Okay? So now suppose I'm holding this thing, but instead of doing that, my Viken system tells me that my fingers are opened by 1 millimeter, right? Now my system ID engine is going to look at that and says, oh, wait, you're not touching the thing, therefore the thing should be falling. But it's not falling. What's going on here? Please explain it to me. And then it has to invent something. In particular, it might invent that the gravitational coefficient is 0 to explain that. So you can see that the very small errors in estimation related to contact could have very large consequences if you actually go through the logic of how physics works. And so we realized that in practice, these things actually do happen. It's really nasty. So we realized that we actually have to optimize the model parameters and the inferred motions together as one big optimization problem. If you don't do that, basically, so what in other words to say is that the objective function in this space is like very oblique and kind of elongated. And if you try to fix one and optimize the other, you end up with chattering that's kind of reminiscent of first-order gradient descent, even though it isn't. So you could be doing second-order gradient descent and here, but the fact that you decouple them is bad. So we realized that we actually have to treat this as a big joint problem. In other words, both state estimation and system identification have to be done together for the purpose of doing system ID. Once you do system ID, you can fix your model parameters, and then you do state estimation online. Okay, so the way we do this, we collect a bunch of trajectory pieces. We put them in one big database. If you look at the Hessian of the corresponding cost function, there's like a band in the middle which corresponds to trajectories. And then there are these dense rows and columns corresponding to the fact that if you have a system parameter like a mass, for example, it's going to affect your predictions at all times. So that's why it shows up. Okay, the good news is that if you do Cholesky factorization of this thing in the right way, you have zero fill-in, so it's very efficient. So basically, the data processing grows linearly with the amount of data you collect, even though you're lumping everything together. Okay? And so once we do that, turns out we can indeed really nail it and get this thing right. Okay, so here's the data collection again. Now what you're going to see is the estimated model, and it's rendering the contact force that it estimated. I mean, this is basically showing that we got the kinematics right. And the next clip is going to show you the optimization in process. So in progress. So these are various cost terms that. These are the residuals that we're trying to match in all kinds of sensors. These are various cost terms that should all become small. This is time during the movement, and you can see that basically gets small in a small number of iterations. Okay, now what you're going to see is the measured versus predicted sensor data here, and they're basically two curves that are completely on top of each other, because we're really getting everything, including these. Let me see if I can pause this. Wait. So you could see that when we touch, there are all these vibrations, and so that's actually for real, because when these flexible structures touch each other, if you put a force sensor there, it's actually going to oscillate. And it's not making it up. It's a real oscillation in the material. The way we get that is by put a stiff spring at the base of the robot, and we can adjust its parameters so we actually get the material vibrations even if we want to. So that's one approach. We can try to do really accurate system ID and state estimation. And the key here is to make it physically consistent. And I'm not going to go into that in detail, but it's a really simple idea. The idea is this. You want to make all the sensor data consistent with your physics model. That means you actually have to take the full complexity of the physics model into account when you do both state estimation and system identification. In other words, if you think of it from a Bayesian inference perspective, all of physics, all your knowledge of physics should become a Bayesian prior for the purposes of computing posteriors. And that knowledge is incorporated into a physics engine, right? So basically what we're doing is we're taking the simulator, plugging it into Bayes' rule, and using the simulator as a Bayesian prior, and then doing Bayesian inference. You can think of it that way. So this optimization of these cost functions, you can think of that as the log of the posterior probability, and the prior behind it is the physics engine, and the likelihood is whatever the sensor noise is, and we just multiply them. This is some cross-validation results showing that this thing is reliable. Now, so that's one avenue, and we have plenty of more work to do along these lines, but at least we now have the tools to, if we really want to get an accurate model, at least for that small system, we can. We're kind of trying to push that to full humanoids now, and we'll see how far we go. I should say it's possible that there's this notion of an observable system, which is kind of the dual of a controllable system. So observable system means that if you start moving the system around and collecting sensor data, is there enough information in the sensor data to infer the true parameters in some ideal sense? And usually that's the case if you buy enough sensors. But in practice, the sensor noise could make it very difficult to disentangle some parameters. So for example, damping and inertia are very hard to disentangle, because both of them cause the system to slow down, right? So you really have to inject like crazy control sequences to really tell you the difference between them. And once you start doing that, your system starts shaking, and you're in a mode that you may not actually be modeling. So the reality can be pretty nasty. In other words, what I'm saying is that just because we can do it for this simple system doesn't automatically mean it's going to scale to a full humanoid. But next time I see you, I may be able to tell you that. In the meantime, we're pursuing another line of work, which is the following. So how to robustify these things. And the idea is to do something called ensemble optimization. So this is a little humanoid called Darwin OP. It's about that tall. It costs $10,000, which is a huge advantage because you can throw this thing around, you can abuse it, you can actually be aggressive. In worst case, you're going to buy another one. The HRP2 that Jean-Paul and company are working with costs whatever, $500,000 or something more than that. So they have 10 people babysitting the robot. So what do we do here? So here's Darwin. We model its mechanics, and we also model its position servos. So the position servos become part of our physics model because that's how the robot works. So the command signal to the robot is a reference position, and then the simulation of the servos and the simulation of the physics are part of the model. Okay? But other than that, the model is not perfect. So the gains and such, the servos are identified well, the full body dynamics is not there yet, and contacts who haven't done this accurate estimation. But now we're going to do this. We're going to say, well, if we build a trajectory plan for this nominal model and we run it on the robot, it's not going to work very well. Indeed, it doesn't. But now we're going to do something slightly different. We're going to generate 10 different models. Okay? We're going to take the nominal model and change the masses a little bit, or change the shape of the foot, whatever, some parameters that we think are important. And there had to be a small number of them. So we perturb them a little bit. And now we have a cloud of different sort of hypothetical robots, okay? 10 of them. And we're going to optimize a single motion such that it's physically consistent for all of them. That is, there exist command signals that will make the robot do that, according to a simulation. And so the idea is that if such a motion exists and it's consistent for all 10 of them, then it probably works for everything in the middle. And that's not a proof, but it's an intuition. And then we just execute this on the system and see what happens. And we actually use feedback at real time to adjust the reference positions, which are the commands. Okay, so here are a few illustrations. Here's a optimization of stepping. And here's the thing boldly running on the little robot. The motion looks quite different because we're not sensing where the root is. We're just sensing the joint angles. So the root can actually fluctuate while the joint angles are very accurate. And it kind of does, so the trajectory is actually quite different from what we planned, but because of this robustification step, the thing actually works. Here's a complicated thing of multi-contact getting up from the table. And so that's work. So these things work about 85% of the time. The other 15% they fall or they get stuck. So it's not perfect yet. I think if we add sensing of the torso, it's going to become a lot more perfect, actually. And now the very last thing I'll show you is some robots are just really hard to deal with. So here's a shadow hand that we augmented with really high-end pneumatic valves and whatever. I just want to show you how fast this thing is. So here we're flexing and extending each joint one at a time. Takes 2.4 seconds to do that. Here's 4 times slower. Yeah, almost done. So this is a pretty amazingly capable robot. It's also very complicated. It has a 100-dimensional state space if you consider all the aerodynamics that you added and the fact that you're manipulating an object. And we don't have a good model of it yet. Nevertheless, we kind of want to control it. And so here's what we're going to do. We're going to design a couple of tasks that have to do either with spinning an object or just achieving a pose. And we're going to do something surprisingly simple that actually works surprisingly well. We're going to build a time-varying linear model of the system dynamics from data without any knowledge of physics. Once we have that model, we're going to apply an optimization algorithm, LQG. It's going to tell us how to improve the control sequence. We're going to apply the control sequence, collect more data, add it to the database, improve the model, and keep going. Okay, here's what happens. Okay, so the task here is to make an object spin around 90 degrees in the hand. Okay, iteration. So each iteration has 5 movements plus a little bit of CPU processing. So this is iteration 5. This is iteration 8. Iteration 0 is nothing. It just maintains pulse, has no idea what to do. It's iteration 10. 13. So it has seen 65. So 65 trials later, it can do that. 15 is 75 trials, it can do that. Which is basically what we asked it to do. Here's a learned movement to do in the opposite direction, another 15 iterations later. And we can also do the same thing in the simulation. So here the learner did not know anything about the physics. So it's just getting sensory data generating motor commands and seeing what sensory data comes in and just building a linear model of the relationship between input and output and optimally controlling with respect to that. And somewhat to my surprise, this thing actually works. It only learns one movement, but that one movement is extremely complicated, and I don't think any of our model-based techniques right now would make that particular robot hand do this, but this local thing does it. The learning is really fast, like I said, so this is a number of iterations. This is a task that I showed you. Each of those is 5 trials, so 60 trials later it has learned. Here's a really interesting thing. If you try to learn a simple task like achieving a pose versus the task I just showed you, it's equally hard or equally easy. So it basically takes the same amount of experience, It's kind of shocking. I mean, this is as simple as it gets. This thing is pretty complicated. This learning algorithm needs the same amount of training data and the same amount of thinking to get it. Why is that? Well, it's because it's local, so it's only learning that one movement. It doesn't know what to do if the object started slightly differently. So in some sense, it's a good way to generate demos, but nevertheless, it's a good one. So anyway, so this is a summary. In the future, what we want to do is take all these optimization ideas and build off-the-shelf software so anyone in this room can use them. And also do more of this transfer of model-based controllers to real hardware. And thank you for listening.
Thank you very much. So we have 5 minutes for questions. Excuse me.
It's about the sensory nature, okay? Because I saw, for example, tactile and somatosensory information in the robot, but I saw no distance sense. For example, no equilibrium sensory and no vision. And for the brain, it doesn't happen just for computing or learning, but manifestly also to have information about space.
So in all the model-based work I showed, there's the assumption of full observability, meaning that you have infinite number of sensors and they're perfect and you've processed all the information and know exactly what's happening, including space and time and everything else. When you go and do it in practice, you work with whatever sensors you have. And of course, we do have vision sensors. So we have Vicon systems that are watching the thing. We have IMUs that are estimating position orientation, which are kind of a vestibular system of some sense. You have touch sensors that you know what you're touching. These days, people in vision are making a lot of progress using depth cameras and LiDARs to get like 3D maps of the environment in real time, which is actually pretty amazing. So yeah, so I mean, we are using every sensor modality that's out there and we're processing it in the most optimal way possible. And it's very important, but my impression so far is that model errors hurt you more than estimation errors. Estimation, you can always get sensing right by adding more sensors. Like sensors are cheap and they're abundant these days, and you can add them. There are no sensors that measure the physical properties of your system, unfortunately, so you can't buy them. So you have to figure it out.
So impressive example, the last one in particular. So this transition towards sensor-based learning, I'm now making the assumption that a human, once it has learned this particular task, and then you give it another, say a larger stick, it would, at first trial, a human would at first trial be able to transfer what it learned.
Probably, and this won't.
And this won't.
Correct. That's why I said this is local. So the earlier things I showed you with the big neural network, that transfers from the first trial to something else, but it's trained in simulation right now. This is trained with real data on a local movement, just one. The good news is that it only takes 60 trials to learn that. So if I had 1,000 trials and I try a bunch of different movements, it's going to generalize. Look, in general, generalization is, there's no magic there. You're not really extrapolating where nobody has gone before. You're really interpolating. Like, there are things that you've seen, and the reason humans are so good is because they just happen to have the right metric. They know how to interpolate, and using some knowledge that which we understood, but we don't. And so I think once, if we can figure out what that space is, it just comes down to interpolating between thousands of examples that we've seen.
And extrapolating?
Sorry?
Extrapolating?
No, yeah, that's what I'm saying. Extrapolation doesn't work. It's, I mean, unless you get the right space, right? So if you know that you have a linear function, sure, you can extrapolate. If it's something complicated, extrapolating outside of that, good luck. All these neural networks that you're seeing these days doing vision and amazing things, they're interpolating, they're not extrapolating. The moment they start extrapolating, all hell breaks loose.
I would like to ask a question about the MPC.
Mm-hmm.
I think the videos you show are really impressive, and I wonder how much effort you spent on tuning the cost function, because you showed some parameters, but in reality you can also change the sampling on the control horizon. You could do
right.
varying
So the
rates.
control horizon is fixed by your computer. Like you always use the longest control horizon that you can get away with in real time. Control horizon versus sampling, that's an interesting question, and in fact you could consider non-uniform sampling, where in the future you sample more sparsely, and we haven't actually done that, but it's probably a good idea. But this is a computational limit. You kind of figure out what it is given the computer and the system. The cost function, like I said, it takes tweaking, which is why we developed a tweaking language. In practice, the guys in my lab can usually get a new task running in 2 days with trying a few things.
Mhm. And very specifically, do you put anything inside for ensuring stability, like a terminal constraint or similar?
So these are two different questions. Terminal constraint usually means what do you do at the end of the horizon when you cannot look anymore. Ideally, you would have some approximation to the optimal value function, where the optimal value function basically says how good is the future starting now. And if you had that, you should put it in. We don't, so we don't put it in. So our terminal cost is just the running cost and nothing else, because we don't know how to build those heuristics. In terms of stability, yes, sometimes you want to take something like angular momentum or some such quantity and penalize it, put a quadratic on it. So these features that I talked about, yeah, that's where human insight comes in. Like you kind of try to guess what are the things that are likely to be important, and you suspect that you have to keep them small and throw them in there. And then after you make that guess, it's a little bit of tuning weights, which is not much actually. But again, I mean, ideally you would start very high level, and the optimizer will discover those. And it does offline, but not in real time.
Would it be possible to use a similar continuation trick or technique to remove self-collision, or would that create too many local minima?
No, we can, I mean, in some of those simulations we have self-collisions included. It will, so the specific continuation trick that I showed you, like you have to declare in advance every contact that you're going to plan explicitly, okay? But you have lots of other contacts that emerge on the fly, and the collision detector is going to respect them and not let you go through them. You just won't be able to do this Jedi trick of, like, so self-collisions, like usually we don't put them in the explicit planner, but it's in the collision detector. So you can collide with yourself, but you cannot be you cannot push on your hair.
Okay.
Yes.
Well, thank you again. It's very impressive presentation, and my question is related to the previous one. Do you, or how do you consider the collision, and are you taking account of the collision in optimization?
Yes. Right. So
may I complete
Yes.
the question by the following benchmark?
It won't work.
Hmm?
It won't work on that.
No?
This is a maze in some high-dimensional space.
No, it's just a six-dimensional space, okay? And
Right.
then this is typically the benchmark we have in motion. Right? The solution is quite easy, okay? And then the question is related to collision avoidance. And sorry, Yoshi, but this is truly to complete, and this is truly a benchmark which is characterized for the computational complexity by the size of the free space that contains the solution and the shape of that.
Yes, I know that. My response is that I know it's a benchmark. I think it's the wrong benchmark, okay. Because look. So this is obviously a dead end, right? So you can make it narrow enough and curved enough so that any method is going to fail. That has no practical consequence on real robots doing real things. Especially in what I'm doing here, the complexity does not come from the fact that the space became too curved. It comes from the fact that there are these intermediate changes in contact, and you're just in a high-dimensional nonlinear space. But sure, if you kind of had to sneak through something really complicated, or if you touch the wall, you all of a sudden get stuck, yeah, it's going to slow down the optimizers. How we treat collisions, we have collision detector. It knows about the geometry. If you touch it, it won't let you go through. We do have this, remember, I had these balls dropping on the floor, and some of them were floating on a cushion. So that's actually an essential thing that we use. We can do remote contacts, like we can do contacts from a distance. And we can make them soft. So we can do something like, if I touch this desk, it won't let me through, but if I'm here, I'm already experiencing some force. And so what that does is, in some sense, related to Katiev's potential functions, but more physics-based. It really prevents the optimizer from getting in trouble by letting the gradient descent sense the proximity to an obstacle. So the way I have defined the physics of contact is actually I've gotten rid of impulsive forces once and for all. They just get really big, but they're always smooth and continuous, and I can differentiate them. And I can even do inverse dynamics with them, and that's actually key to optimization. So yeah, I mean, I agree. I know that benchmark is bad, which is why I stay away from it.
So a last question, and then we move to the next speaker.
Thanks, Emma. That was very impressive as usual. I'm not sure I fully understand the CI, the contact invariant optimization. Can you include in that properties that I'd like to have at the contact point, like say passivity?
Passivity, what exactly do you mean by that?
Passivity meaning that I can take the system and I can wiggle around any way I want, but I can't get any energy out of it continuously. That's key to establishing contact stability and so forth.
Right. So energy is... This contact model will not, I'm pretty sure it will not let you steal energy from the system. The reason I say that is because whenever we mess up the physics and there's a way to cheat, the optimizer immediately discovers that and starts cheating. We've seen incredibly crazy things that reveal that there is a bug in the physics, basically. So if it doesn't discover a way to extract energy from the system, that probably means that there isn't one, or it's very hard to find. I haven't specifically analyzed what that does to passivity, but yeah, I think, I mean, you can so we have a friction constraint, so you can never pull on a contact, you can only push. So I think that already gives you passivity right there. I mean, you're going to get a force opposite to velocity, right? So you're going to get negative energy injected by the contact. But it's hard. I mean, once you go to this optimization-based formulation of contact, it's actually surprisingly hard to prove that energy is not being injected in the system. And it requires assumptions that may not be true, like Lipschitz things.
Thank you very much.